area of infrared astronomy and his leadership role in turning infrared astronomy into a fundamental tool for understanding astronomy and astrophysics. Dr. Becklin has been at the forefront of astronomical discovery for more than 40 years. I'd like to highlight only a few of his important scientific discoveries. Dr. Becklin's early contributions included the 1967 discovery and recognition of the importance of the Becklin-Neugebauer object, a massive protostar in the Orion molecular cloud. Now, you know, not very many astronomers have a celestial object named after them. In 1968, a year later, Dr. Becklin and his collaborators discovered infrared emission from our Galactic Center, which he observed using higher spatial resolution instruments to detect many stellar sources in what's now recognized as the central cluster of massive stars at the center of our galaxy. Skipping ahead, in 1983, Dr. Becklin, working with Ian Gatley and Mike Werner, discovered our galaxy's central circumnuclear disk, which is now recognized as a model for the central disks in gas-rich spirals and as a reservoir for the material accreting onto the central supermassive black hole. Over the last 3 decades, much of Professor Becklin's research has focused on the search for brown dwarfs and debris disks. In 1988, he and Zuckerman discovered GD-165b, the first new spectral class of dwarf star found in the past century, and probably the first known brown dwarf. Finally, in addition to his research, he's held several major leadership roles. These included director of NASA's Infrared Telescope Facility in the 1980s, being vice chair of the Astronomy Department in the UCLA Department of Physics and Astronomy. Professor Becklin and Dr. Ian McLean began instrumentation of the Infrared Camera Lab at UCLA upon their arrival there in 1989. In the 1990s, Professor Becklin led the NASA proposal to develop and operate Sofia and subsequently served as a chief scientist. I'd like to concluding by just noting there was a quote which was from Ralph Waldo Emerson that was one of Professor Becklin's nominators used to describe his career. And the quote is, "Do not go where the path may lead. Go instead where there is no path and leave a trail." And Professor Becklin has certainly done that. Anyway, congratulations. I'm going to go over here now. One more. Okay.
Now, how do I change the...
Yes, we'll get, and this is your talk, and you can push these buttons, and it goes from this one, and this one goes forward, this one goes backward.
Okay.
You good with that?
I think I am.
Okay.
Thank you. Thank you, Christine. And I'm Eric Becklin. I'm the Sofia Chief Science Advisor, and I work for USRA. I wanted to get that in right at the start. They pay my salary. I'm also Emeritus Professor of Physics and Astronomy at UCLA. So just an outline of what I'm going to talk about. This is pretty much chronological. I'm going to talk about the early days at Caltech, some of the discoveries that Christine just made. Then I'm going to talk about working on the Kuiper Airborne Observatory in Hawaii and director of the IRTF. Then moving to UCLA, the Large Keck Telescope, large infrared arrays, and adaptive optics. And then finish with talking about Galactic Center orbits, which is work I've been done most recently with the people, Andrea Ghez and Mark Morris at UCLA, and the massive black hole in the center of the Milky Way. And finish talking about Galactic Center and other unique science with Sofia. And that's, I'm presently the Sofia's Chief Science Advisor. Okay, I want to thank the AAS for this very prestigious award. I'm really, really, really honored. And I'm pleased that you all took the time to come and hear me. I hope you enjoy it as much as I enjoy talking about what I've done in the past. I really, there are several themes that I want to today to have you watch for, and one of them was just mentioned. New technology drives a field of study, and that's certainly been true for me, and so watch for that. Also, it helps to work with good people. That really is important. You can't always have that, but it really does help. And the most important is really enjoy what you do. Enjoy the discoveries that will come, because they will come. Thank you. Okay, so the early days of infrared astronomy. As a young student at Caltech, I was lucky enough to work with Gary Neugebauer, who you've all known. He won this prize, I think, in '96. And he was a young professor at that time, but he went on to do the work, a lot of the work I'll discuss, and I actually worked with him throughout my full life, his full life. He passed away, unfortunately, 3 years ago. And he was also director of Palomar and really started the Keck telescope and IRAS, the IRAS satellite. And Bob Layton. Bob Layton didn't win this award, but he could have. Bob Layton was a physicist who was just extremely talented. Just at the time I started working for him, he and his students had discovered solar oscillations on the sun, the 5-minute oscillations. And he also built this 2-micron sky survey that Gary and he were building, that I was lucky enough to become part of that team in the summer of 1964. Gary gave me the job of finishing a photometer that had been, so that it worked on optical telescopes, a simple infrared photometer, and particularly at Mount Wilson, but maybe also at Palomar. And it was to follow up the 2-micron sky survey. I will talk about the sky survey later in more detail. And I was lucky enough because I loved working on the survey. It was fun to go up there, but it also allowed me to make other additional observations. Just as an added point here, besides graduate students, and there were several of us working on this, there were a number of undergraduates that actually worked on the sky survey. I see one of them there, Ed Groth, Tom Seufer, Dan McCammon, and Jerry Nelson, who built the Keck telescope, and Doug Osheroff, who won the Nobel Prize at Stanford. They were all undergraduates working with us, so it was just a fantastic time. Okay, so the first thing we did, that I did, was to look for protostars in the Orion Nebula. When we got the survey going, Layton said, we gotta find protostars. Well, we saw the Orion Nebula, all right, but our beam on the sky survey was 2 arc minutes, so we got the nebula, all the stars. We didn't pick up anything. But we had this new photometer, and I went up to the 60-inch, and we decided we should just scan across the sky in the region of the Orion Nebula. I looked in the eyepiece, I saw the trapezium. To the south, I saw the nebula and Theta 2, and I thought, well, we'll just scan north. Now, nobody knew anything about molecular clouds or anything about what was going on at that point. I should say the optical astronomers thought we'd not even discover anything in the sky survey. So, you know, we were just out there looking. So we had a 9 arc-second beam, a 13 arc-second beam, and we scanned with steps of 9 arc-seconds. I knew nothing about Nyquist sampling, so I just knew we had to move less than the beam. And on a 6th scan, we got something almost as bright as Theta 1c, with no optical counterpart at all. Now, this was obviously very exciting, and I'm going to show you the first scan. Here it is, and it's on a strip chart. Most of you don't know what that is, but time runs along the bottom. Oops, I got to be careful as I move the cursor. Time is going along here, so you're scanning along here, and then all of a sudden you get this peak, and it goes back down, and that's time. Most of the time it was just flat. In fact, I saw Theta 1c, and then basically nothing till this. So this was exciting. However, and this was in January of 1965, they had already started the 2-micron size survey. However, Gary and I didn't know what to do with just this one object. And we actually sat on it for a year. I was trying to pass quantum mechanics from Zachariasen at Caltech. And believe me, that was more difficult than discovering the BN. But I did it. However, a year later, Guido Munch, who many of you know, he's still alive. He lives down in San Diego. He was in the lab. He was working with Gary. And he saw this and he said, "Holy crap, Eric, that's the most interesting thing I've ever seen." And it was more expressive than that. And he said, "You got to go down to Palomar and get more data on this." So we went down to the east arm, got 3.4 and 1.6 micron photometry. We saw it was extremely red. We got Jim Westfall to make 10 micron measurements, so we got a full spectrum. The new source was about 1 arc minute northwest of the trapezium, a temperature of 600 degrees, and we suggested it was a forming star, a protostar. Now, Guido's graduate student, Richard Larson, was working on infall calculations, so Guido had him come over and take a look at this. When he saw it, this really helped him say, wow, maybe my calculations really mean something. So that was nice. It also led Frank Lowe and Doug Kleiman to observe the region at 20 microns. Frank was over there. He took it right away, went to the telescope, and discovered the famous IR Nebula at 20 microns. Published a paper on 1 wavelength result, but he was right. Everything was right about it. So it's a very nice story. Here is in the lab with Gary. Okay. Gary is on the left. I'm in the center, and Gareth Wynne-Williams, who worked with Gary and I in the early 70s, and then also later worked with me in Hawaii, is on the right. And that's in the middle is a photometer and a dewar. That's the thing that we put on the telescope either at Mount Wilson or up at Palomar. Okay, the next big discovery that I was involved in was the Galactic Center. And that was detecting radiation in the near-infrared of 1.6, 2.2, and 3.4 microns. Layton was the one who, again, just like the protostar, pointed out that we should do this, and he started with the survey and told Gary, go get the coordinates of SAD-J star, the radio source, because that's where it's likely to be. However, there was a transformation problem. Actually, make sure your coordinates are always correctly precessed. That was the problem. Wrong precession, and this is all written up in a book, in an article that George Reiki and Frank Lowe wrote a few years ago, and I wrote it and had Gary okay it. I don't want to go any further into it, but needless to say, it was a major mistake, and they did not find it on the sky survey. Although it's there, believe me, it's there. However, I had done M31 on the 60-inch, so I knew how red, and I knew the reddening, and I knew how bright M31 was. And Dan McCammon had just built a new field lens that would allow us to have bigger than a 13 arc second beam, up to 1.5 arc minutes on the 24-inch. And I knew we could see this. So we located the position of maximum brightness at the position of SAD-J star on the very first scan of the 24-inch telescope. And the next slide shows that. One of the scans, this isn't the very first one, didn't actually hit the real peak on the first one, but got it later, obviously. But this shows it, and this was very exciting. I knew now that I really had something, and we had something very important. And we had it not only at 2.2 microns, which this is, we had it at 1.6. Again, this is a strip chart. In this case, we just let the telescope drift by. Okay, so we also, did follow-up work on the 60-inch and Palomar 200-inch telescopes. And the color of the fluxes at 2.2 and 1.6 when looked, and then compared to what stars should be, looked like there was about 25 magnitudes of visual extinction, or about 2.5 magnitudes of extinction at 2.2 microns. Visually, that means that the extinction was 10 to the 10th in the visible, 10 billion. At 2 microns, it's only a factor of 10. So, and we knew the extinction fairly well because of Johnson's work at Arizona. The extinction that we measured was a little bit more than the nominal 2 magnitudes per kiloparsec that people quoted for the average in the Milky Way. Now, equally important than the fact that we had detected this, we actually compared it to M31, measurements we made at Palomar, and then scaled for the distance and the reddening, and without any correction factors, we got the following. Now, this is a normalized scan of M31 on the top at the resolution shown there. That's about 2 arc seconds at Palomar. And then the bottom we had to, that's from the 24-inch on the Galactic Center, and I had to integrate the map some. They don't have exactly the same shape, and they have been normalized to 1, but the peak is within a factor of 2, and the shape looks quite similar. When I showed this to Alan Sandage, before we had the paper published, he looked at it and said, "Wow, Eric, Walter Baade would have given his eye teeth to make that observation." That made me feel really good. Anyway, Alan worked with Gary and I on a further paper of M31 in the Galactic Center, and I always loved Alan for his enthusiasm for astronomy. Okay, the next thing I want to talk about came from the 2-micron survey, and it's IRC plus 10^16. It is unquestionably IRC plus 10^16. It has a survey number. Is the most important discovery to come off the 2.2 micron sky survey. There's been over 1,000 papers written on this one object alone, mostly in the radial line and continuum and infrared line and continuum. It's a hugely bright source, as you'll see. The sky survey that was Layton built is shown in the center there. It's at the Smithsonian out at the airport. You can go out and see it. It was built by spinning epoxy, and that was Layton and his genius. Liquid epoxy, it would settle, and it formed into a parabola, had a focused image with a beam of about 2 arc minutes, and we had about 5 arc minute detectors. We also had, in addition to the 2.2 micron detectors, we had a 0.8 micron detector, with a little bit bigger, but IRC plus 10^16 was so bright, so red, was so red that the 0.8 micron signal wasn't coming from IRC plus 10^16, it was coming from a nearby star. That made it appear that it wasn't quite as red. It was kind of in the middle of our red sources. Well, when I was going through the list, I got to this one, and I put the source on the 10 micron detector. It wham went up off the strip chart, and that's shown on the right there. All the others, I could have predicted what this was going to happen. This one was just hugely a factor of 10 off of what it should be. I was so excited as I found this that I called Gary Neugebauer, and Gary always called on the mountain to see how things were going. That's just the way he was. And in this case, I called him. But I was hyperventilating. I was so excited. I knew this was really something. Follow-up studies that we did, Harry Hyland and Gary and others on the 60-inch at Mount Wilson indicated that this object was the brightest object in this solar system at 5 microns. Now, we didn't do a survey, but we just surmised that. So here is some pictures of it. On the left, it's in the optical UV. And IRC plus 10216 is a nearby variable carbon star. It's only 100 parsecs away, and it's losing mass at an extremely high rate of 2 × 10⁻⁵ solar masses per year. It's a dust and carbon factory in space. Harry Kroto studied this in the radio. He was an astrochemist and looking at long carbon chains, and he got to 12, and he wanted to get 14 and 16 carbon chains, and he went to Smalley's lab in Rice, and in that, looking for the long chains, they discovered C60, and of course, they just got the Nobel Prize for this. Now, you may say, well, how do you know that that was connected? Well, Harry asked me in his last book to write a 3-page appendix on this discovery because he felt that this was what led him to C60 and buckyballs. So I make the statement that this is the greatest discovery of the 2-micron sky survey and led Harry Kroto to discover buckyballs. And many observations continue today. There's thousands of papers, and tomorrow B.G. Anderson will be talking about the image on the right, which is polarization vectors, very radial, and we'll be very interested to see what the model is of what causes those radial vectors, and that's at 10:30 a.m. tomorrow. Okay, the next thing I want to talk about is the Kuiper Airborne Observatory, Hawaii, and the IRTF. The Kuiper Airborne Observatory was a 0.9-meter IR operating on a C-141, started operation in 1974. And Mike Werner led a team of Ian Gatley and myself that made a number of discoveries. We worked with Al Harper as well, and we had multiple wavelengths. But the most important thing we did was do the Galactic Center with a 30 arc-second beam and a resolution at wavelengths of 30, 50, and 100 microns. And the next slide shows the results. This is a discovery of the supranuclear disk in the Galactic Center. And it shows 30 microns is just centered on the Data Sagittae star, which was known at that time. And then at 50 microns, it's kind of an hourglass shape. And then at 100 microns, it's 2 blobs. And the only way we could interpret this was a disk along. By the way, the galactic plane is running. Let's see if this works now. Does not want to. Okay, the galactic plane is along here. This, by the way, is 3 arc minutes up and down. And the only way we interpreted it as a gas ring around the Galactic Center. I'll come back to this when I talk about Sofia results in just a minute. Okay. The other thing we did on the Kuiper Airborne Observatory was to observe the sun and the extreme limb of the sun at 30 to 600 microns. We wanted to measure the height and temperature of the chromosphere. So we flew 2 successful missions in 1981 from Japan and 1988 from Guam. And we did determine the height and temperature, and this is all in papers, Lindsay et al. Most of it's, one is Rolig et al. But we covered all of these bands. And the main characters on the eclipse are shown in that picture. I'm on the left. Mike Werner, who is the project scientist on, or was, still is, on Spitzer and many other. He was the main PI on the experiment. And on the right is Charlie Lindsay. And Charlie Lindsay was the solar astronomer of our team. And he has this patch over his eye, so you'll wonder why that is. It's because it's not a patch, it's a neutral density filter, because he was looking at the sun in the visible as the eclipse was taking place, and he didn't want to burn his eye, and he wanted to stay dark adaptive. Charlie is a genius. He really, truly is a genius. Can't go into all the stories, but we did determine the height of the far infrared and submillimeter continuum, and it was a factor of 2 higher, and that's shown on the very right there, a comparison of the functional wavelength on the bottom and height that from the prevailing models of the sun, the VAL models, and they were corrected later. Charlie and John Jeffries assured me of that. The continuum temperature was also carefully calibrated and measured by our team, and it was lower than what the Concorde had measured about 5 years earlier when they did this same type of experiment. So we felt very good about this result, and it was a real plus for, and as far as I'm concerned, in how you can use airborne astronomy to do unique observations. Okay, in the spring of 1977, John Jeffries, the director of the Institute for Astronomy, offered me a position at the Institute for Astronomy to be the division chief of the IRTF. I came to Hawaii in July of '77 and started working with Jerry Smith, Hans Bosgaard, Jim Harwood, and especially Rich Capps. I hope Rich is in the audience, because he's a great collaborator, and he really helped me get the IRTF scientifically going. But there were many others as well. And one of our primary focus was to get 5-micron images of Jupiter to support the NASA Voyager flyby. And this was actually a congressional mandated result that we needed. And many people at NASA said it couldn't be done, couldn't get the telescope, and you wouldn't, even if you did, you're not going to be able to do it. But Rich Capps, particularly Rich Capps, and graduate students, Chaz Beichman, I believe, and Dana Backman are both here, and many others, showed them wrong with 5-micron images 2 months before the second flyby in May. The flyby occurred in July, so we actually helped the support. And this is the image. It's 5 microns of Jupiter, and that dark regions in the center that are very black are holes in the atmosphere of Pluto where you're going down and seeing high temperatures. And this is very similar to what you see in brown dwarfs, and it was this that actually led to the brown dwarfs' understanding of having holes in the clouds and made their spectra so weird. But we got the data. I'm very proud, and thank you all that worked on that experiment. Okay, just some pictures from those early days. On the left is Jerry Smith, who is a project scientist, one of the best. He also did Keck and IRAS, and myself. And then in the middle, on the right, in the very center at the bottom is John Jeffries. I'm behind him, and Rich Capps is over on the right. Kind of has about the same amount of hair as I do. And you'll recognize some other people there, Sidney Wolf, Dale Cruikshank, and Dave Morrison. Okay. One of the things that happened on the IRTF that I did a lot of good work with a large number of people, but from my standpoint, one of the best discoveries was the first L-dwarf in late 1980s. Ben Zuckerman, who is here, thank you for coming, Ben. And I used the IRTF to search for possible brown dwarfs around white dwarfs, and one cool companion was found around the white dwarf GD165, and that's a Nature paper. It's a resolved point source at a distance of 4.5 arc seconds, which is 120 AU, and a temperature of 2100 Kelvin, and a luminosity of 10 to the minus 4. Other stars that were known at that time were 10 to the minus 3, so much more luminous and had higher temperatures. And we did show it was a physical companion later. Spectra by Kirkpatrick and Henry showed a very red spectrum with very strange features and was clearly the first L-type dwarf, and Kirkpatrick acknowledged that. So GD165b was the first classified star in over new classification, an L classification. So in over 80 years. And it was also probably the first imaged brown dwarf or object outside this solar system. Okay, next I want to talk about moving to UCLA, the IRT detector array revolution, a Keck Observatory, and the Galactic Center. Mike Jura invited Ian McLean and I to UCLA in the late 80s to start the IR Lab and get involved with Keck. A revolution was occurring in IR arrays. They were now coming on board, they were getting bigger, and there was also a revolution in large ground-based telescopes. UCLA wanted to get involved in the detector development and the instrument development and in telescopes. So Mike Jura had the insight to see how this would happen. He's shown in the center, or the left picture there, and unfortunately passed away 2 years ago. But he knew how to get this done. Ian came with experience and knowledge building instruments, and he just won the Weber Award 2 days ago for the work he's done. He built MOSFIRE, the instrument that was talked about in the previous talk, and many of the Keck infrared instruments. I had experience in IR observing, running the IRTF, and I had followed the Keck Observatory development with Jerry Nelson. There was another revolution that was occurring just at this time in ground-based astronomy, and that was adaptive optics. FlareMax and others at the observatory and other observatories were developing this, including adding laser guide stars, and you can see the lasers pointing out to Sagittarius star out of the 2 Keck telescopes. FlareMax is on the right. Turns out that the infrared from 1 to 5 microns is the best and easiest place to do this correction because of the longer wavelengths, and therefore the atmospheric coherence doesn't have to be as good. There's also an advantage due to just the structure of the atmosphere, the coronagraph, the cosmograph that helps. Diffraction limit on the Keck 10-meter telescope was obtained at 2.2 and 3.7 microns. So the next slide shows the revolution that occurred as a result of this. On the left is the first image done with the IRTF of the Galactic Center, and actually the first science paper using IR arrays, done by Bill Forrest, Judy Pfeiffer, and Wayne Stein, and that's at 3.7 microns. They also had an image at 2.2 microns, and they have an X for Sagittarius star. On the right is 18 years later on Keck, the same region. Every source you look and see is there. They're scaled to the same, but there are hundreds and maybe 1,000 objects on the right. And the integration is the time. That is a revolution. It's like going blind to actually starting to see what's there. Sagittarius star is marked with a cross in each case. The Forrest et al. Is a little higher. So they had the position off just a little bit. But obviously a revolution. So this revolution led Genzel and Gez and their teams to follow orbits of stars around the radio source Sagittarius star for over 20 years. And they jointly won the Crawford Prize in 2012 for convincing evidence of the massive black hole of 4 × 10⁶ m sub sun at the very center of the Milky Way. The measurements included both proper motion and radial velocities, and both teams also detected variable radiation from the position of Sagittarius star, which I will talk about in just a minute. I was fortunate to be a founding member of the Gez et al. Team. Okay, so this, now I have to get started, is the Orbital Movie that most of you have seen, but I want to show it again. Right there, 16 went around the black hole. There went SO2 around the black hole, moving at about 3% the speed of light in both cases. SO2 is now progressing. By the way, 1 second is 1 year here. And it stops just at 17.7. And you can see in 18, it's going to again go 3% the speed of light. So the Keck and VLT orbits are the strongest evidence for a massive black hole in the Milky Way. It's 4 million suns. The distance is 8 kiloparsecs, and we now know it to a few percent in both of those. Two stars, SO2 and SO16, were going 3% of the speed of light as they went close. In March, April of this year, SO2 will again have closest approach and be moving at that speed. By the way, Andrea's on the left, Mark Morris on the right, and then the whole team is on the right. Mark wasn't there, but I'm in the back. But I am a second-order person on it, but I love this team. And during 2018, the Galactic Center group will be ready to measure the gravitational redshift of SO2 as it comes out of the gravitational potential, and that will be about 200 kilometers per second, and we'll measure it at 5 sigma. And this will be a space where the gravitational redshift in terms of the mass has not been measured before. Obviously, this is measured in white dwarfs, and it's been measured by the pulsars, and now with the LIGO, but not at this mass of 10 to the 6th. Okay, variations of Sagittarius star at 1.6 to 4.5 microns. I'm going to have to go through this quickly. I want to show this movie of Keck that I have to get started again. And this is the same region, a little bit smaller than you just saw. And you see that Sagittarius star is both red, and it moves up and down kind of in a, that was about 1 second per hour, so it comes and goes down about every hour. So when Giovanni Fazio saw this, he said, you know, Eric, I think we can measure this with Spitzer. And I said, well, I'm not sure, but I did look at Eric Tolstrup. He had a 3.5 micron image as well as the forest image. However, he had contours, so I could actually calculate how much guiding error there would be with Spitzer. And sure enough, they had gotten the tracking on Spitzer good enough that they could really get this measured. So with the Giovanni's team at CFA and IPAC, UCLA Galactic Center group, we all put in a proposal for several periods of 24 hours to measure the 4.5 micron data. And to our surprise, we got the beautiful curve on the top. We were doing it to test a proposed dust cloud. G2 is supposed to cause the variations to go up. Typically, there are 4 of these peaks per day. This one actually has 6. Sometimes there are 2. In the X-ray, there's only 1. But we now have some, there is no effect with G2, and we have some fabulous coordinated Spitzer and Chandra data that is going to be coming. We have the data, and it'll be showing actually that there is a correlation. It's very interesting. I don't want to say anything more about that. Okay, the final thing I want to talk about is the program I'm working on now, and that's Sofia. And I want to talk about it from the eyes of my view as the chief scientist. I want to start by talking about a ring of dust and gas orbiting the Galactic Center black hole, 4 times 10 to the 6th, and a possible connection with AGN. And I also want to talk about some brand new results using a new polarization camera, Hawk Plus, on an AGN at Z of 3.9. And then finish with star formation in Orion and polarized dust. Okay, there is Sofia. It's a 2.5-meter telescope. in a 747, and you can put big instruments on, and it really works extremely well, as you'll see. And it takes instruments up into the stratosphere safely and brings them down, and we have 10-hour flights. Okay, so the revolution in detectors and telescope size was happening in the thermal infrared and airborne astronomy as well. Remember that Galactic Center image I showed you before? Now on the right is a Sofia image of that same region, and you can now see a ring in a faint outline, and this is with the Hawk Plus camera. We'll also do imaging with forecast, allow it all, and I'll discuss that paper. And FIFI-LS, Kraba et al. Has some beautiful data. Even GREAT has imaging data. So there is a revolution in the circummolecular ring science. Oops, I'm sorry. Did you see this while I was talking? Sorry. All right, I'll just quickly say, because this thing doesn't work very well, but that's the Kuiper, and that is the same region, but now with Sofia. Completely different, and I'll talk about these detailed differences in just a second. But it does clearly show a ring. And this, now I want to talk about the connection to AGN. So this is the Lau et al. Image that is the highest resolution of the circumnuclear ring. It is situated around Sagittarius star, which is right in the center here, right below that white spot. There is that white stuff going in. That's been known for a long time. That's ionized gas, and it has hot dust in it. That's why it's white in this presentation, which is 1931 and 37. I want you to look at the orange or the yellow-green stuff that's in a circle outside. That's what's the most important. It's almost a perfect 1.5 parsec radius ring, and it's seen in coolish dust of about 100 degrees Kelvin. The white stuff is like 200 or 300 degrees Kelvin, similar to what you get from H2 regions. And the disk is tipped on the sky by 23 degrees. So remember, the galactic plane runs along that ring, and then it's tipped. And the ring is resolved, and it's small. It's about 0.3 parsecs in width. And its diameter is 1.5 or 3 parsecs. So it's 10 to 1 in the ratio. And it has some interesting structure along it, almost periodic in nature. Now this is just a cartoon to show you so you don't get misinterpreted. On the right is what we see when we look, and we're seeing the inner part of the ring. The outer part is seen at the longer wavelengths in this, the molecular emission. And if we were looking down at the top of the galaxy, we'd see a ring like you see in the left-hand side. So now that you understand the geometry, let's look, to me, the similarities that this might have with classical AGN. It's a dust and gas disk surrounding, oh, by the way, it's rotating around the galactic center. So it's actually rotating, so it goes away in the north, so redshifted at the north. And that's the same way that the galaxy rotates. The dust and gas disk surrounding a massive black hole is a donut and gas 3 parsecs in diameter. Outflow and radiation that will be coming from that central region should preferentially go actually out perpendicular to that disk. And Alfred Kraba, I want to thank for pointing this out to me. He may not have remembered that he did, but he certainly did, because I had always thought of it as being more uniform in terms of the infall and outflow. But there are directions. With inflow is along the plane, outflow is perpendicular to it. So this explains the ionized gas will also be in the plane, and that's why the ring is not as uniform as it gets shadowed in terms of its heating. It's being heated by young stars that are in the very center. Why they're there is a whole other question. That's the ones we track, and we don't know why they're there. There is one difference between a classical AGN. There is no jet going out, and there is no high luminosity portion of that jet. The AGN Sagittarius star is 10 to the minus 9 L suns. Even though there's mass going on to it, you have to talk to the theoreticians like Ramesh, I forget his last name, but he's at Harvard. You know who I'm talking about. But the dust and gas, to me, looks similar. We obviously need more study with Sofia of this very important region at high JCO, ionized carbon, and O1, and we will get that. Now, just to make the point on the comparison, this is an image of a typical AGN from Meg Urey and her collaborator. And she has this disk of a classical AGN, and that disk is the same size, it's the same density, and the only difference is her AGN, there's mass falling on and it's creating this major outflow. Okay, I just quickly want to say that that's the closest AGN. It's a dwarf, but we can do great work on it, and I think we have. We've also detected a high Z galaxy at 3.9 with Hawk Plus, and that's shown on the image on the right. That's at a wavelength of 89 microns, and oops, there it is on the right. Sorry, almost did it again. But there's a beautiful image at 87 microns, clearly seen. That's with half an hour of scanning with the Hawk Plus. This is not polarization, but it was done at 53, 89, and 154 microns. And we use scanning where you just kind of move the telescope around and then correct for it afterwards. It all seems to calibrate and do very well. This is near the limit. Of course, we had 10 to 1, but we can do a little bit fainter if you want to spend time on it, because it does integrate down. But these make measurements of this Z of 3.9 galaxy, which is lensed. There's a galaxy in front that makes it brighter, at 11, 18, and 31 microns, so rest wavelength. So you can start talking about what the AGN components associate both with the AGN and the hot dust. There were two other galaxies higher than Z of 3 that were measured as well that I know of, and they both came from Planck and Herschel. Okay, I want to end by talking about star formation in the Orion molecular cloud, and this will be quick so that I will finish on time. This is the image on the left is a visible image from HST, Odell. The middle is a near-infrared from ESO from Mark McCaughrean, and on the right is a Sofia image, and you can see how different they are. In the middle, near-infrared, you start seeing BN and some molecular outflow, but on the right, you see the bar of Orion, and you see the Kleiman low nebula and BN object, and it's now separated into individual objects. I don't want to say anything more about that. There are several papers written on that. I do want to mention this, though. In addition, Hawk Plus now is measuring magnetic fields, and this is due to the grain alignment. And there have been several talks here, and there are people you can talk to about how the grains get aligned. But the advantage is you can get the magnetic fields, and in the far infrared, because the grains get aligned and then they emit in that aligned position. Magnetic field is perpendicular to the electric vector. I've seen the 53 micron polarization map, and I tell you, it is spectacular. I can't say anything about it because I don't even understand it, but it is spectacular. So look for it. All right. Learn more about Sofia at the town hall at 7:30 to 8:30 today. It's in Potomac D. Make sure you're there. We want to fill the room with as many of you as there. And in summary, Sofia has produced outstanding science. We have nearly 100 publications, spectacular Galactic Center results, as you see, discovery of many chemical and astrophysical lines that I haven't discussed. Hawk Plus polarimetry is just getting started, and we've measured Z of 3 galaxies. We have Pluto, Triton, and MU69 occultations, and we have over 20 PhDs, and they're increasing every year. Sofia now is the only facility offering routine use of community 28 to 300 microns, right between JWST, it stops at 28 microns, and OMA. There we sit, and we offer the community this availability for the next decade or more, hopefully much more. All right, going back to lessons learned and a thank you. Work with good people, that's important. Science advances follow the new technology, and that's really very important. Getting the data correct is the most important for us observers. That's none of ours. You gotta have good data or you got nothing. If you don't have good data, you can have all the theories in the world, but make sure that it's correct. Finish the project or the paper, if at all possible, and get papers written, because unless a paper is written, you haven't done anything. You've got to have written papers, and you've got to have citations coming as well. So you need all of that. Most important also is enjoy the excitement of discovery. I have, and thank you to all my collaborators, students, colleagues, and support people, including the funding agencies, NASA, NSF, and the private institutions, and even my competitors. I haven't mentioned them, but there's Arizona and Cornell and Chicago, and you know, we're all in it together. But I haven't even mentioned space, and space is just, there's a revolution happening in space, and we know that from JWST and Spitzer, and the future is bright. Thank you. Oh, I have to thank my family who have found me gone much of the time. I'm sorry. Thank you.
Spectacular. That's great. You want to take a question?
Pardon? Yeah, I'll take questions.
Is anybody lining up for a question here?
Okay.
Yes? No? I think then we will just congratulate you again. Tell you that was wonderful.
Thank you. Thank you.